Hello everyone, welcome back to my channel. Today let's go over a hard level question that I just solved on my own. So I'm super happy about this, and I'm extremely glad that I was able to come up with my own solution to this problem without any assistance. So let me show you how I did it. This one is 220 contains duplicate 3. So basically you have an integer array nums, and the question is pretty simple. As long as the indices are not equal, and these two criteria are satisfied, return true if we can find such a pair, and false otherwise. So basically, my first brute force approach that got time limit exceeded was just following the instructions. So if I is not equal to j, then if absolute I minus j less than or equal to index diff, literally just copying this, and nums of I minus nums of j is less than or equal to value diff, return true. Otherwise, if you loop through all the pairs and can't find anything, return false. So this is going to work, but it's n squared, and that's going to be a little bit too slow for a hard question with such a low acceptance rate. So let me show you how I came up with an optimal solution from this. So just walk you through my thought process. So basically, if you make some observations, the index difference less than or equal to, that means at maximum the difference can be 3. That means the sliding window has to be of size this plus 1, because if we think about it, let's say the index difference is 2 at most. So if we're on a current element, let's say we're somewhere here, if the index difference is equal to 2, then at most we could land here from here, or we could land here, right? So we could land at most here. So if we just use a sliding window of size 3, which is 2 plus 1 equals to 3, then we can basically just try to compare to see if any of the neighboring elements are satisfying this value difference, because if they are, then this is also hit. So that's the idea. Sliding window of size index diff plus 1, index diff plus 1, and then I'm going to use a nice tool called a sorted list. You've probably seen it used in my channel before. So basically, we're going to get every window of size index diff plus 1. So let's go ahead and say this is nums of index diff plus 1, and let's print SL. So that basically makes it so that everything is already in sorted order. This is a balanced binary search tree, and in this case, the whole thing is index difference, because 3 plus 1 is 4. The whole array is of length 4. So we're just going to loop from 1 to length of SL, because we're only doing this once. So the time complexity is acceptable. The difference is just SLJ minus SLJ minus 1, absolute difference, because again, since they're already in sorted order, then we can just compare the current to the previous to see what the closest difference between any two pairs are. In this case, it's 0, right? So if diff happens to be less than or equal to value difference, we can go ahead and return true, right? Most cases, it's not going to be the case. Fine. So let's go over length of nums minus index diff. So remember, sliding window of size index diff plus 1. Usually it's plus 1, but not in this case, because let's just say cur is nums of I plus index diff, and let's print cur. This is probably not going to be of the same size as we want SL here. So notice that we want 1 bigger, so it's going to be plus 1, actually plus 1. So this is actually plus 1, because that's going to be the size that we're looking for, right? 3 if this is 2. So what this tells us is, if we want the thing in sorted order, and this is what I came up with, is we're going to add nums of I plus index diff and make sure they're the same size. So if I plus index diff is less than length of nums, then we can add that element. Okay, so, and obviously we're going to have to discard the one to the left. That's the definition of a sliding window. Cool. So this -1, -1, because this is already made of the size 4 in the case of 3. So that's why, let's see here, SL. Let's see. We just want to make a sorted list of the same thing. So let's do this. Okay. No, that's not it. Let's see. Coding it up without bugs can be hard. Okay, there we go. Perfect. So now you notice this is just a sorted list copy. So something clever that I did was I said, okay, if we're going to insert, let's say this was 19 before, and we're going to insert 5 to 159. Sorry, this is an array. If this is the new location, that's the only new number being introduced. And if in sorted order, we know that the adjacent neighbors are going to be the ones that are going to be compared, why don't we get the location of nums of I plus index diff, right? Because that's the new location. It was inserted at 1 because the sorted list uses a binary search tree and a binary search part of the name to find the exact location in order that the element should be inserted at. So because of this, that makes it so we can just compare the left to location. Let's say location is index 15, left of location 10, right location index 29, index 01, and then that will see if the difference between any of those and 5 is less than or equal to value difference, right? So if the length of SL is bigger than value or location, then we can say the difference is, or if absolute value of SL location -1 minus SL of location is less than or equal to value diff, return true. So the left side, and then the same thing on the right side, right? Minus SL location less than or equal to value diff, return true, right? Otherwise, at the very end, we can return false because this is the only thing that's been changing. Otherwise, we're just discarding. So if we discard, there's not going to be any difference, right? So let's run this. Okay. So, location +1, let's do that. Okay, and let's submit it. Okay, so first of all, if length of SL is bigger than 1, then just go ahead and do this. So maybe we don't even need this. Okay, so we're getting close now because this did take me some experimentation. So the previous minus the current. Or we can just say if location -1 is less than length of SL, if location +1 is less than length of SL. Okay. Okay, there we go. So left and then right for each one has to be separate. Okay, cool. So let's submit this. And there you go, passes all test cases. So again, I'm super happy that I was able to come up with my own solution to this problem without any help and solve it completely on my own. So that's it for this video. Thank you for watching. And if you enjoyed, please consider subscribing and stay tuned for more.